In this video, I want to show you how chemical risk assessments are done for food by using a very simple example that will also pull in that 1 in a million number that we've talked about a little bit. So the example is going to be the Exxon Valdez oil spill back in 1989. After the oil spill, there were a lot of native Alaskans who were subsistence consumers of seafood, and they needed to know quickly whether there was a cancer risk. So they put together a task force, and I'm going to show you one small piece of a larger risk assessment they did. So you will see at times there will be numbers that seem trivial. That's just to keep the example simple. So they identified the problem, and the problem was that there was a risk of developing cancer due to exposure to polynuclear aromatic hydrocarbons, PAHs. And they appeared in all kinds of seafood, but the example we're going to use is in the bivalves that you're looking at here. So the hazard came about because of the reasons that you're looking at here. We don't have to deal with them. Let's just basically say that PAHs have been shown to increase cancer in animals. They bioaccumulate in the flesh of seafood, and humans consume seafood, or in this case, bivalve mollusks. So here is a little summary statement of the hazard identification, and the hazard was exposure to PAHs. So the second piece of a risk assessment, chemical risk assessment, at the time was called the dose response assessment. This is now something that we would call the hazard characterization. But let me give you a quick lesson on dose response curves. You would have some actual data from experiments or from accidental exposures in the environment, and basically what they give you is a dose on the horizontal axis and a response on the vertical axis, in this case an excess tumor rate, more tumors than would occur naturally. So each point is an experiment. You'll notice that there are no doses in the low range because most of these data points were obtained in animal studies by giving animals doses of these chemicals. So there's an absence of data in this range in here. So what we do is we get whatever points are available and we fit a curve to them. This is a stylized curve, by the way. I just freehand drew it, so don't expect great graphics here. So this would be our best estimate of the dose response curve. But we know that these limited number of data points are from a sample, and if we took another sample, even using the same dosages, we would expect to have a different alignment of points. And so we use classical statistical techniques to identify the upper confidence limit on this dose response curve. And that's all well and good, but you'll notice that we have no data on the low dose range there. Beyond our last and smallest experimental dose, we have no data. So how do you fill that in? Well, it turns out that in the United States, most of our agencies say you take the upper confidence limit and you take the 0,0 origin, and taking the 0,0 origin means we make an assumption that there is no threshold. There is no amount of this chemical that is absolutely safe. Even one molecule has some small cancer risk. Then we get a ruler and a pencil and we connect the 2 points. There are, of course, other ways that might be more mathematically accurate, other ways to extrapolate, but they're generally not used. So in this particular example, when doing real-time risk assessment in Alaska, to get the dose response curve that you're about to see, this task force did a survey of the data that was available and found one study, a rat study. And that rat study gave them this red point up here that you see in the upper right. It said 0.11 milligrams per kilogram daily lifetime dose of benzoapyrene has this level of excess tumors. This is the proportion of rats that develop tumors. So we had a data point, 1 point, and we had a no threshold assumption, 0, 0, and we had a ruler and a pencil. So we connected 2 points to get a dose response curve. Generally speaking, you have much richer, much better dose response curves, especially these days. The Environmental Protection Agency defines something called the unit risk, and that is the slope of this line. The unit risk is telling you what the risk is associated with 1 milligram per kilogram daily lifetime. So here's how we're going to use this. Slope is rise over the run, and the proportion of tumors, if you pull it off of what I just showed you, was 0.18, and the dose, the run, was 0.11. And that works out to 1.63. Not quite the 1.75 that we're using, because there was rounding that went into using this simple example. But I know some people like to look carefully at the graph, and if somebody checks me, they'll find out they can't reproduce 1.75, so I stick this in here for those nerdy people like myself. So back to here. What we would like to know then is what's an acceptable level of protection. This is where the 1 in a million comes in. So let me come on back here. What we want is the equation for this line. Now you may or may not remember the equation for a straight line is mx plus b. So the slope is 1.75, that's the unit risk. The intercept was 0, so the equation becomes 1 equals 1.75 times x. Now, y is the proportion of tumors, and we are willing to accept 1 in a million. That would be an acceptable level of risk. If we have more than an increase of 1 in a million, that would be unacceptable. So we plug 1 in a million in for y, we solve for x, and we now have a dose. So if this dose here is exceeded, then you will have more than 1 in a million chance of developing a tumor. Okay, so if you could imagine, if we were being very fine here and I could identify 10 to the minus 6th on this vertical axis, and if I could look over to the curve and drop a perpendicular down to my horizontal axis, that would be 0.57 nanograms per kilogram of body weight daily for a lifetime. That would be the value of the dose that we just identified. So we used one data point and a no threshold assumption, a 1 in a million lifetime upper bound, and we found out that this was the daily dose of benzopyrene over a lifetime that would cause no problems. No problems meaning the risk of a tumor would be less than 1 in a million. Now, in Alaska, they used an average weight of 60 kilograms per person. So we took the 0.57 nanograms per kilogram times 60 kilograms and said, okay, as long as the Alaskans are consuming 34 nanograms of benzopyrene or less, they will be safe. And again, safe is a judgment. It's not a fact. It's not a scientific fact. Safety is not a fact. It's a judgment. And the judgment used here was that 1 in a million chance of developing a tumor. So now we move to the exposure assessment. This would be how much benzopyrene are the Alaskans consuming. So here is where my warning about this is a small piece of the risk assessment becomes important. Because for the remainder of our example, we're going to take the average daily intake of bivalve mollusks. And the average was 2 grams per person per day. Well, 2 grams is about the size of your little fingernail. So that's clearly not very much. And this average included eaters and non-eaters. But we're not doing a high consumption analysis right now. Typically what would happen in a risk assessment is that you would use a high consumption level. You would take a person who's at the 95th percentile of eating bivalve mollusks, and you would use them as the test case. But this is how the risk assessment was actually done, so I'm going to remain faithful to that. An oil spill has lots of different chemicals in there: benzopyrene, idenopyrene, benzofluoranthene, and they are all different chemical structures, but you can express them all as a benzopyrene equivalent. So these are the conversion factors. So the deal then was to go out, harvest some mollusks from the grounds, analyze the flesh of those mollusks, find out how much of each chemical is in there, and calculate the equivalent number of benzopyrene in a gram of flesh, multiply it by 2 because we're using a mean of 2 grams. And so for the mollusks, the average level of PAHs consumed is 30 parts per billion of benzopyrene. So 2 grams times 30 parts per billion equals 6 times 10 to the minus 5th when we do the conversions for you. This is not the units that you usually work with, but this would be 60 nanograms of benzopyrene per person per day. So now we move on to the risk characterization step. We compare the exposure to the 1 in a million risk. So for a 60 kilogram adult, we say the risk is less than 1 in a million and is therefore acceptable if less than 34 nanograms per day are consumed. But we just found out that Alaskans consume 60 nanograms per day. 60 is bigger than 34, so you would certainly think that this advisory council would have said don't eat the bivalve mollusks. But it turns out that they did not, because previous oil spill data showed that the area restores itself after 10 years. So if we're looking at an average lifetime of 70 years in '89 for these Alaskans, and for 10 years they're going to be exposed to these chemicals, what this task force did was they used 10 divided by 70, or they said you're only going to be exposed for 0.14 or 14% of a lifetime. So they took 14% of the lifetime exposure. That's equal to 8.4 nanograms per day. Then they said, oh, 8.4 nanograms per day for a lifetime is less than 34 nanograms per day for a lifetime, so it must be okay. And if that makes you feel queasy, then I'd say that makes you very normal, because this is not science, this little adjustment that they did here. But what they did was they published some advisories and let people go. So here's the takeaway for this. This is a simple example of basically what's done for chemicals that are unintentionally in our foods or in the environment. So for methylmercury, you would use a method like this, where you would get a very detailed and much more sophisticated kind of dose response curve. You would find the 1 in a million risk for that, find out what is the acceptable dose, and then you would do a study, an exposure study, find out what people are eating, what kinds of fish, what the amount of methylmercury was in the fishes, and then you would array that data, find maybe the 95th percentile, a high level consumer, see what they are consuming, compare that to the 1 in a million risk. If that 95th percentile consumer was consuming more, then was considered to be safe in that 1 in a million way, then there would be restrictions placed on marketing these fish. If it would be close or less, then what you would tend to have would be advisories, advising people not to eat the fish or how much fish to eat. So that's how the 1 in a million and the chemical risks of chemicals that are unintentionally in the environment would work.